Hello, and welcome to another episode of Math, Music, and More. Today we're actually going to talk about linear algebra and matrices. And I want to talk a little bit about matrix multiplication and what it does to vectors, but really spend time on what's actually happening, especially in a visualization of what transpires when you actually operate on a vector, so that we get a little bit of an intuitive feel graphically as to what's happening in the vector space. But interestingly, at the end, I then want to sort of turn it on its head and talk about what vectors are actually doing to the matrix. That'll be sort of the punchline at the end, which I find incredibly fascinating and an interesting insight by someone that I'll introduce you to at the end of the episode. So let's start. Matrices, pretty simple. You have a 2 by 2 matrix, for example, that multiplies by something like x and y. And the simplest example, of course, is something like the identity matrix, which is 1, 0, 0, 1. And you all probably know matrix multiplication already if you're watching this video. And you know that doing this, you just take one of the x and none of the y's. Therefore, you're left with x over here. Then you take none of the x and one of the y's, so you're left with a y here. So as the name implies, this is the identity matrix. So we'll start with that. Anytime you have a vector where you go over x, and you go up y, which means this is the resulting vector, x, y. If you actually multiply it by the identity matrix, it doesn't change. Okay, so what are some of the other matrices that we could actually look at? One type of matrix would purely just either expand or contract the vector. And a simple example of that would be something like just changing this to a 2 and changing this to a 2. As you can imagine, what would result is that we get 2x and 2y. So in this case, instead of going out this amount, you go out this amount. Instead of going up 1y, you go up 2y. And what you see is that it's really just a doubling of the length of the vector, and hence the magnitude or the absolute value of the vector. Okay, so that's pretty straightforward. But what else can actually happen? Because it's not always so perfectly clean where you have, zeros on the off diagonal. In those cases, you can sometimes have pure rotations. And let's think of some very, very simple examples, just that we can envision exactly what kind of rotation could take place. Well, a moment ago, we started with the identity matrix, right? What if we were to flip things around a little bit? What if we were to have 0, 1, 1, 0, and if we multiply that by x and y? In this case, when we perform the 2 by 2 matrix against the 2 by 1, you get 0 x's and 1 y. So that means the top component would be y, and then 1 x and 0 y's. So this would be x. But what does that actually mean? Just draw the vector, and you can immediately see what kind of picture emerges. If we were to have a vector that goes across 2 and goes up 1, this would be the vector. However, if we were to flip that, then we actually only go over 1 and go up 2. Then this is what the resulting vector would look like. This one here would be xy, this one here would be yx. What kind of rotation is that? Can you visualize it? It's really just a reflection about the line y equals x. So that's a kind of rotation, and it all depends on what vector you're actually starting with. Let's do another one just so we can continue to visualize how this actually works. What if we were to make one of them negative in that opposite diagonal? What if we were to take, 0, negative 1, and 1, 0, and we were to multiply this by x and y? What would we get there? There's a bit of a glare, so I'm going to stretch the solution way over here. Well, we have 0 x's and then a negative y, and then 1 x and 0 y's. And let's again use the graphical representation of vectors in a vector space to understand what kind of rotation was that actually. Well, in this case, if we use the example as we did before of going over 2 and going up 1, right? This would be the xy vector, over 2 and up 1. Again, just using a simple example so that we can visualize what's happening. Well, now, instead of going over 2 and up 1, we will actually go over negative 1 and up 2. This is negative y x. And what happened there? As you can guess, it's perfectly orthogonal. We actually did a 90-degree rotation. If you were to make both of these negatives, I bet you would end up with something in the exact opposite direction. Well, let's check it. Let's check it. It would be negative x, negative y, so we'd go negative 1 and 1, 2, negative 2. Yep, that's where you end up. So, interesting stuff that's happening here. So you're picturing the rotations, and this gives you a little bit of a sense as to what matrices are actually doing to vectors. They can stretch vectors, they can contract vectors, they can rotate vectors, and they can do both simultaneously. If you were to have something, again, that doesn't have any zeros in the cross diagonal or in the other diagonal either, if you just had something like, for example, 2, negative 1, 0, 1, right, times xy. Well, then you'd have 2x, right, and then minus y, and then 0x and a y. That's going to start stretching the vector and rotating it at the same time. Now, because this video is getting so long, I'm going to jump to something that I found fascinating, which is it's not just about what matrices do to vectors, it's also what vectors do to matrices. And what do I mean by that? It's something that I saw in OCW, Open Courseware, of 1806, 18.06, Michael Strange, or Strang, however you pronounce his last name. Great professor that I think unfortunately passed, but he was at MIT for ages and ages and ages. But he said something very interesting. He said, you know, when you're looking at a 2x2 matrix, like A, B, C, D, and you're multiplying it by x, y, you could think of A, B, C, D as two column vectors, AC and BD. And when you multiply it by the vector xy, go ahead and check this for yourself. It's the same thing as just multiplying x by AC and adding y times BD. So what are you actually doing then? You're actually taking this vector and creating a linear combination of these two column vectors. And this is fascinating to me because it means that if the columns are independent of each other, linearly independent, if you evaluate AC versus BD, one is not some sort of multiple of the other, then these two columns can form a basis for the entire 2x2 space. So it's fascinating. Yes, matrices act on a vector, and the matrix is the operator, the vector is the object, but you can also think about it the other way around. The vector is the operator, and the matrix is the object. It's a set of column vectors that establish a basis for the entire R2 space. Anyway, if you're interested in that, go ahead and check out, like I said, Gilbert, I don't know if I said Michael before, my apologies if I did, but Gilbert Strang, 1806 OCW, Open Courseware. Fantastic stuff if you're on the treadmill running and trying to find something to do with your brain while you're stressing your body. It's great stuff. Anyway, thanks everybody. Like and subscribe, and I hope you found this all helpful. Take care. Bye-bye.